In this video, we're going to study the concept of a function, which is the most important concept in precalculus as well as calculus. We saw in a previous video that an equation induced a relation between the variables x and y. And a function is also going to be such a relation between the variables x and y. However, we're going to add a certain restriction, namely it's going to be a relation with certain special properties. We start by looking at the definition of a function, and we note that we always define a function as a triplet, namely you're always going to have to provide the two underlying sets for your function, the set A, which we're going to call domain, and the set B, which we're going to call the codomain of a function. And a function, given these two sets A and B, is going to establish a relation between the elements of the set A and the set B. So let's look at an example. So let's say that I have the set A made out of the elements 1, 2, and 3, and then my codomain, the set B, made out of the elements, say, A, B, and C. Given these two underlying sets, I'm going to define a relation between these two sets that's going to give me the function f. And let's say that f is going to assign the x value of 1 to A. It's going to assign the value of 2 to C, and it's going to assign the value of 3 also to C. So, given this example, let's try to understand the definition. Let's go back to the definition and think about it a little bit. So, as I said before, we define the phrase a function f from A to B. You always have to have the underlying sets A and B given in order to define a relation between them. The next thing that is part of the definition is what kind of an object is a function. And as I mentioned before, a function is a relation. We're establishing a relation between the elements of the set A and the elements of the set B with two special conditions. And here they are. So a function is going to assign every element x in the first set A. So every element in the set A needs to be assigned, and this assignment has a second restriction, namely it needs to be assigned to exactly one element y in the set B. This y we are also going to denote, and this is called function notation, by f of x. So let's see what this means more precisely. So we note that the x value of 1 is being assigned to the y value of A, and that's quite a mouthful to say or write. So therefore, we're going to have this function notation, namely we say that the function f assigns the x value of 1 to A. And that's why A, which is our y element, is denoted by f of 1. Similarly, since 2 is being sent to C, we have that f of 2 is C, and finally that f of 3 is also C. Now, looking whether or not this particular relation defines a function, let's see if both conditions are satisfied. Namely, what are these conditions? Every element in x needs to be assigned. Both 1, 2, and 3 were assigned, so that condition is satisfied. And each of these elements needs to be assigned exactly one element y. Well, 1 is only assigned A, 2 is only assigned C, and 3 is only assigned C as well. So both conditions are satisfied, and therefore this relation here represents a function. Right. Now let's write a few remarks from this definition that are going to better enable us to remember these different parts of the definition. So the first remark as I said, if you have x being sent to the element y by my function f, then we have a specific notation for this particular y value. This is the function notation, namely y is going to be f of x. Right, so if 1 is being sent to 3, we're going to have that the y value of 3 is f of 1. In terms of the two restrictions, we note that the first restriction was that each element x in A must be sent to an element y in B. So when I look in the set A, every single element in that set must have been assigned to a corresponding element in B. The second condition is that no element x in A can be sent to two or more elements y in B. So this assignment tells us that each x must be assigned to exactly one element y. We can't have that one x is being assigned to 2 or 3 y values. So given these two conditions, let's look at some examples and determine if the following relations give us a function or not. So let's say that I have the sets A made out of the elements 1 and 2, and the set B made out of just the element A. So is this particular relation a function? And the answer to the question is no, because our first condition is not satisfied. Namely, there is an element x in A that is not assigned to an element y. So therefore, this is not a function. Namely, the element 2 is not assigned to a corresponding y value. Let's look at another example. Let's say that I have the set 1 and 2 for A and the set 4, 5, and 6 for B. And let's define this relation by sending 1 to 4, 2 to 5, and 2 to 6. So this is how I define my relation. And now the question again is this a function or not? And we notice that while 1 is sent to only 4, 2 here is sent to 5 and 6. So we have these splitting arrows coming out of 2. So again, we have that this is not a function because one x value, namely 2, is being assigned to 2 or more y values. Looking at another example, let's say that I have the set A made out of the elements 1, 2, and 3, and the set B made out of A and B. And I define the following relation. I'm going to send all 3 elements, namely 1, 2, and 3 all into A. So now the question is, does this represent a function? Well, let's check the two conditions. Is every single element in A being assigned a corresponding y value? Yes, so this condition is satisfied. How about that no element x can be sent to 2 or more elements y in B? Well, looking at this, we notice that 1 is really being sent to only one y element A. 2 is being sent to one y element A again, and 3 is being sent to one y element A. So also the second condition is satisfied. Notice the difference between here, where we did have a violation of the definition of a function where 2 was being assigned 2 y values, so 1x sent to 2 y values. Here, there are multiple x values sent to the same y value, but that is not a problem. It does not contradict the definition of a function, so this happens to actually be a function. So two perhaps easy mistakes to make. So let's continue with our remarks. Let's say remark 4. We note that some elements y in B may in fact be matched with more than one element x in A. And that certainly is possible, namely the y element of A was matched with the x elements 1, 2, and 3. That is allowed. And finally, we want to notice that some elements y in B may not be matched with any elements x in A. And we notice here that was the case of this element B. No x element was sent into it, but again, that is not a requirement of the definition of a function. Let's look now at one more example where we're going to write the relationship. We're going to represent it with ordered pairs. Let's say the ordered pair 0, 1, the ordered pair 0, 2, and the ordered pair 3 and 4. So this is another way to represent a relation, but let me show you how to basically rewrite this using our old technique. So we have 0 being sent to 1, then the same element of 0 is being sent to 2, and then I have that the element of 3 is being sent to 4. So this is just another way of representing a relation using ordered pairs rather than these diagrams. So the question here is, does this relation define a function? And the answer again is going to be no. This is not a function because one x value of 0 is being mapped to y values of 1 and 2. Now that we have a better understanding of the concept of a function, how does this relate to our usual functions, the polynomials, quadratics, rational functions that we're so used to? Well, the idea is that we usually work with A and B as infinite sets rather than finite sets. So this idea of representing a function through these diagrams is not practical. So let me give you an example. Let's say we're dealing with the function f going from R, the set of real numbers, into the set of real numbers, namely A is the set of real numbers and B is also the set of real numbers. And what I'm going to do is provide you with what you're used to, namely say a function rule. And I was talking earlier about having the need of having 3 elements to define a function, namely the domain, the underlying set, in this case R, the codomain, namely the set R in this case, and the so-called function rule. These 3 together really define a function. You can't just say function rule gives you a function. You must know what your underlying domain and codomain are. So, in terms of the connection between these types of functions and what we just described with diagrams, what can we say about that? Well, let's see what would I like to do if I were to try to represent this function through diagrams. Well, let's say I have the x value of 0, and I can compute that f of 0 with this rule is 1 minus 0 squared, which is 1. So this rule tells me that 0 is being assigned to 1. let's pick another x value, let's say 1, and then I will have 1 minus 1 squared. So I know that 1 is being mapped to 0, and then I would have to think about 2 and 3 and 4, but there are infinitely many numbers, not just the integers, but 1.5, 1.1, square root of 2, etc. I can't really list them all and draw arrows because I'll never complete my task. So for that reason, because it's so impractical given infinite sets to represent my function through this assignment with arrows, what we do instead is we provide you with the rule, and I'm giving you the tool to figure out what particular arrows go from what x values to what y values. You want to know what happened at x equals to -1? Well, you're going to compute f of -1, which is 1 minus -1 squared. 1 minus 1 is 0. So the x value of -1 is assigned to the corresponding value of 0. And this is what this function rule gives us, and why we don't typically represent functions as diagrams. However, the same underlying idea is present here. Important topic in understanding the concept of a function is the graph of a function. So the graph of a function, let's write a short definition, is like in the case of equations, the collection of all ordered pairs xy with the property that y, I can compute y by plugging x into my function, and we want x to be in the domain of my function f. So if I look at a specific graph of a function, let's say this, this is the graph of the function f. What have I represented in this Cartesian plane? Well, just like in the case of equations, out of all the points in the Cartesian plane, I have selected those with the property that the x and y coordinate of any point on that line satisfy, namely the equation y equals to f of x. So as an example, let's see that I give you the function f going from r to r, and f of x is x squared. The graph of this function is a parabola going through the origin, and again, if I take any single point on the graph of this function of, say, coordinates x and y, what is the connection between the x and the y coordinate? Well, they must satisfy the equation that y is x squared. So if I have the x coordinate, say, of 1 here, the corresponding y coordinate would be 1 squared, namely 1. Another point on the graph would be 2 and 4, or 3 for the x coordinate, and 3 squared, namely 9 for the y coordinate. It is also important that we understand the connection between the concept of equations and that of functions. We both saw that there were, in fact, a relation between the variables x and y. However, the concept of a function satisfies additionally certain special properties, so it is a more restrictive class of relations. In particular, the important property is that no two y values have been associated, can be associated with one x value. To be able to distinguish graphically whether or not a curve, for example, this curve over here represents the graph of a function or not, we developed a test, namely the so-called vertical line test. We're going to see in a minute that this vertical line test is simply a restatement using the graph of the definition of a function. So let me first state the vertical line test. We say a curve in the Cartesian plane is the graph of a function if and only if no vertical line intersects the graph at more than one point. So in this case, looking at this particular curve, what we're after is finding a vertical line. For example, there are many, but this is one vertical line that crosses my graph at more than one point, namely twice, and therefore this is not the graph of a function. So this is not a function. It suffices for us to find one such vertical line that crosses the graph at least at 2 points, and we are certain that we're not dealing with the graph of a function. On the other hand, to see that we are in fact dealing with the graph of a function, let's say that I'm dealing with this particular curve, what I need to do in order to test that this is the graph of a function is to run an imaginary vertical line throughout my graph and check that in fact no matter where I am with this vertical line, the vertical line crosses my graph at most at one point, and therefore this happens to be the graph of a function. Let's look at one last example. Let's say that we're dealing with the equation of a circle, and we note that this does not, using the vertical line test, represent the graph of a function. This is not a function. It is an equation, namely the equation of a circle, but it's certainly not the graph of a function. We note that in essence this vertical line test is really a restatement of the definition. Why? If I assume that, say, this x-coordinate over here is 1, and let's say that there is a y-coordinate over here at height 2, and this one over here has height -2, then what we're noticing here is that I have the x-coordinate of 1 being mapped to both the y-coordinate 2 up here, which is why I have this point on the graph, and to the y-coordinate down below at -2. So what we're dealing here is one x value being assigned to y values, and that contradicts the definition of a function. So in essence, if I have my vertical line intersecting the graph at 2 points, like we have in this case, what happens here is that one x value, right, namely this one at 1, has been mapped to both 2 and -1 two y values, and that certainly contradicts the definition of a function. So in this section we'll learn to think theoretically about the concept of a function. Namely, we understand it is a relation but with special properties. Namely, we want to avoid that one x value is being mapped to 2 or more y values, and that every x value in the set A, the domain, needs to actually be assigned a corresponding y value. The graph of a function is simply the collection of all points in the Cartesian plane with the property that they satisfy the equation y equals to f of x.